Okay, so hello and welcome to our video lecture for today. So we are going to proceed to the liquefaction as a geotechnical hazards. So as for our learning objectives, at the end of this session, you will be able to describe the mechanism of liquefaction, discuss the effects of liquefaction on soils and structures, explain the methods of reducing soil liquefaction hazards, and then describe distinct phenomena in liquefaction, and then at least you can list 3 remedial measures on liquefaction. So for our approach, for a better understanding, we are going to have a zoom lens approach. So we're going to start with the farther concepts until we get closer to the topic wise. So the key definitions you need to understand first is the Phreatic Zone. Okay, so this is actually called as the zone of saturation. It is a part of an aquifer below the water table in which relatively all pores and fractures are saturated with water. And then above the water table is the vadose zone. The Phreatic zone size, color, and depth may fluctuate with changes of season and during wet and dry periods. So we can see here the cross section. So of course there are catchment areas, and then water will percolate on what we call, if you could recall, that is termed as the catchment area is the watershed, and then percolates and moves underground. Okay, so yung zone of saturation is below the water table, as you can see, and the vadose zone is the upper portion of the water table. So we also have the capillary fringe. Why? Because there are lines and fractures underground in which there is a capillary phenomenon. Yung ibig sabihin ng capillary, there is a rise in waterhead. Okay? Kapag tinusok mo yung tubig, especially with the small tube, small diameter tube, the tendency is to rise. Okay? That is the principle. So moving on, we need to understand the pore water pressure. So the pore water pressure is sometimes or often abbreviated as PWP. So it refers to the pressure of groundwater held within a rock or soil in gaps between the particles. The gap between the particles are called pores. So there will be a pore water pressure below the phreatic level of the underground water are measured with piezometers. So this is a vertical pipe. The vertical pore water pressure distribution in aquifers can generally be assumed to be close to hydrostatic. So later on in your soil mechanics, geotechnical engineering, and hydraulics, you can expound your knowledge about this. So in the unsaturated zone, or what we call the vadose or the upper portion, the pore pressure is determined by capillarity and is also referred to as tension, suction, or matrix pressure. So there are two types of pressure, in which I'll expound it in a while. So pag positive pressure, the pressure is above the value of the atmospheric pressure. So usually that is measured below the water table or the sea level. Kapag bumaba tayo, Pag bumababa tayo, tumataas yung pressure. At pag umaakyat tayo, nagiging negative yung pressure. Meaning, as we go up, we are having a negative pressure. Kapag negative pressure, ang ibig sabihin nun, suction or pahigop. Okay? So, on the other hand, kapag positive yung pressure, the pressure is bursting. Okay? So, that is about pressure. Pore water pressures under unsaturated conditions are measured with tensiometers, which operate by allowing the pore water to come into equilibrium with a reference pressure indicator through a permeable ceramic cup. So when we say permeable, nape-penetrate siya ng tubig. So it is placed in contact with the soil. So the importance of pore water pressure, it is vital in calculating the stress state in the ground soil mechanics from Tersagi's expression for the effective stress of a soil. So later on, you're going to discover this. So the pressure in the pore is greater than atmospheric pressure, it is positive. Okay? So yung line ng zero, no, na pressure, yung water, okay, or yung sea level. Okay? Yung sea level, that is zero pressure. Zero gauge pressure, no? Pag tumaas tayo doon sa sea level, that is negative pressure. And as we go down, that is positive pore pressure. So above the water table, soil remains unsaturated and the pressure in pore is lower than the atmospheric pressure. By the way, the value of the atmospheric pressure is equivalent to 101.325 kilopascal. Hence, it is said to be negative pore pressure. So what is good in the negative pore water pressure is that there is a phenomenon of capillary rise. By the way, bakit ba tumataas ang tubig kapag tinutusok natin ng isang tube with a small diameter? So this phenomenon is actually because of the surface tension. Ano bang ibig sabihin ng surface tension? Imagine nyo na yung surface ng water ay para siyang isang film. Kapag mataas ang surface tension niya, pwede kang maglakad sa tubig. Pero, surface tension is not that great to resist the forces. So, as an example of that is, kapag yung blade, hiniga mo pa higa or pahalang in a water, that will float. That is because of the surface tension. Pag patusok mo naman nilagay yung blade, of course, it will sink. And what is good in that is when we have just right amount of water between soil particles, we'll have a holding mechanism for these soil particles. The negative water pressures specific to unsaturated media have a mechanic effect of bringing together the components of the porous medium. Pero, pag nasobrahan yan, it will completely fill the water and it will burst out, separating those particles. And that is excess pore water pressure. So, excess pore pressure refers to a sudden increase in pore pressure within a soil due to a rapidly applied loading conditions under undrained loading. So in a while, I will also discuss undrained and drained conditions. Okay. So moving on, materials with low permeability such as clay, may exhibit this behavior. So, of course, mahirap i-penetrate yung clay. Okay? It's almost impermeable yung clay. However, in a long state or a long condition, clay would absorb water pero mahirap niyang ilabas. Meaning, it will take years for clay to be drained. So, because of its low permeability characteristics. Okay? That is the character of clay, and that is not good. So we will expound that by and by. As it has been already presented, in the unsaturated soils, very strong interactions between water and soil particles develop. In granular cohesiveless materials such as sands and gravel, these forces are explained by absorption and capillary phenomenon. In cohesive soils like clay and silt, the nature of the interaction is more complex, involving inward chemical links. All of these forces are known as soil-water interaction forces, and their intensity is expressed by the soil suction, or it is often called as matrix suction. So of course, we would not like to have an excess pore water pressure. So typically, in practice, there are provisions of drainage that will reduce the excess pore water pressure. So as you can see in the diagram, if we are going to have an engineering intervention, especially in a site where we have high groundwater level, when it rains, of course, ayaw nating dumiretso yan sa baba because it will loosen the foundation of this slope material. And of course, what is the result? Circular slip failure. So, circular slip failure, mag-i-slide yan in a circular form. So, what we do, intercept natin yan or redirect the water. That is done through a permeable drainage system, in which by and by, I will give you an example. Okay? So another term you need to understand is the confining pressure. Confining pressure. Pressure applied equally on all surfaces of a body. So just like if you are going to dive below the ocean, sabi nga natin below the water level, nagiging positive yung pressure. And the pressure is a bursting force towards the object, okay, in all direction. So remember that, in all direction. That is why there are divers na nag-aalangan kapag napakalalim na ng trench na kailangan nilang sisirin, dudugo na yung kanilang tenga because of the high pressure. Okay, so you can see here that pressure is acting on all direction. And as we go below the water level, the pressure increases. Okay, so moving on, cyclic loading and cyclic fatigue. So cyclic loading, ito yung paulit-ulit na stress. Okay? It could be with reverse loading or without reverse loading. What do we mean by that? So, kung pataas lagi ang loading, paulit-ulit na pataas, that is without reverse loading. Pero pag paulit-ulit na pataas, tapos in-applyan ng paulit-ulit na pababa, that is cyclic loading with reverse forces or loading. So this can cause cyclic fatigue. So the best example for this one is if you're going to bend tie wire or yung alambre, if you're going to continuously bend that, applying a reverse force, pataas pababa, it will break. And that is because of the cyclic fatigue. So it can be defined as the stress, strain, and deformation induced in a material by cyclic loading. Okay, so that is a cyclic fatigue, as you can see in the picture. Okay, so moving on, we are now getting closer to the real topic. We have here drained and undrained condition. So drained condition, the pore water can easily drain out from the soil matrix. So what are the examples of this one? Yung mga coarse material. Okay? So yung mga coarse material is identified as sandy soils. Yung mga sandy soils, malalaki pa yung grain size niya. That is why enough lang yung pore size for water to penetrate. So you can easily drain it out. So water can be easily drained from that material. Unlike soils with smaller particles or fine-grained materials such as silt and clay, ito na yung undrained condition wherein mahirap pigain ang tubig. So the condition, the pore water is unable to drain out, or the rate of loading is much quicker than the rate at which the pore water is able to drain out. So what is the implication of this? Pag in-applyan mo siya ng loading, kapag kino-compress mo siya, mas mabilis mag-transfer yung loading than water to be drained out. So what is the implication of that? Malambot yung lupa and your foundation will fail. So take note, no matter how stiff is your structure, it will be subjected to failure if your foundation is that weak. So it is better to have a geotechnical or a good geotechnical investigation or subsurface exploration. Okay, so moving on to the topic, we have here soil liquefaction. Soil liquefaction occurs when a saturated or partially saturated soil substantially loses strength and stiffness in response to an applied stress, such as shaking during an earthquake or other sudden change in stress condition in which material that is ordinarily a solid behaves like a liquid. In soil mechanics, the term liquefied was first used by Allen Hazen in 1920. Transactions of the American Society of Civil Engineers. So this is the reference. So 1918 failure of the Cavalleras Dam in California. He described the mechanism of low liquefaction of the embankment as okay. If the pressure of the water in the pores is great enough to carry all the load, it will have the effect of holding the particles apart and of a condition that is practically equivalent to that of the quicksand. Alam niyo ba yung quicksand? Yung kumukunoy. The initial movement of some part of the material might result in accumulating pressure. First on one point, and then on another successively, as the early points of concentration were liquefied. So for us to have a better understanding, that looking at the simple diagram here, the basic mechanism of liquefaction in a deposit of loose saturated sand during earthquakes is the progressive build-up of pore water pressure due to cyclic shear stresses. So kapag lumilindol, the loading is cyclic. It will cause cyclic shear stresses. So before liquefaction, you can see that there is contact between the soil particles. Now, kapag nag-separate yan, what will happen is that lulutang na yung mga soil particles. And there will be no effective stress. Okay? So that is why the soil material will be liquefied. So when we say liquefied, it will flow. Okay? Imagine yung lupa nagfo-flow. Ibig sabihin, para na siyang at liquid state. So it is already in the liquid state. Okay? So we can see here the behavior of the mechanism. So initially, if we have a structure lying on the loose sand, meron niyang effective stresses. So effective stresses with saturation. Okay? So loose sand yan na compact. Of course, kapag may structure dyan, the loose sand will tend to consolidate. So consolidate meaning nadidrain yung tubig kapag loose sand. Kapag clay, mahirap madrain yung tubig, and that is too bad. Okay? So stable pa lang siya dito. However, when a seismic load will occur, it will disintegrate the structure of the soil. Why? Because magkakaroon siya ng exit points dito. Kung may tubig yan, ano bang nangyayari? There is a capillarity or capillary action. So ano na nga pala yung capillary action? Pag tinusok mo yung tubig, tataas yan. Okay, because of the pressure. Okay, and surface tension. So combinein mo na yung pressure at surface tension. Those material will go up. And what will happen? Maglulusen yan. Okay. So yung compacted sand dito, maglulusen. Because tumaas nga yung ibang volume ng lupa. And then, mapupuno na ng tubig. So, mas marami ng tubig kaysa sa lupa. So, what will happen is that subsidence of ground. Malambot yung lupa. Okay? So, that is... So, we can see here, loosely packed grains, pore spaces filled with water. Okay? Before the earthquake. During earthquake, grains push apart by upward flow. So, the loosely packed grains, okay pa lang yan kasi pack pa rin siya. Although may tubig, there is a soil integration, meaning magkakadikit pa yung lupa until be liquefied. So the result are sand boils, sand dike, sand injected into overlying cement. Okay, so this is earthquake induced liquefaction. So the triggering factor is the earthquake. So the phenomenon is most often observed in saturated loose sandy soils. This is because a loose sand has a tendency to compress when the load is applied. Dense sands, by contrast, tend to expand in volume or dilate. Ano bang ibig sabihin ng dilation? Kapag umapak ka sa beach, magkakaroon ka ng footprint in the sand. Yung outline ng paa mo on the upper or the perimeter of your feet outline, yun yung nag-dilate. Ibig sabihin, tumaas yung mga soil particles because of the loading. Of course, mas mababa dun sa area ng paa mo. Okay? Because the load is concentrated on the area itself. So there will be a migration of the volume. So that is the best example on how to explain the dilate. Okay? So if the soil is saturated by water, a condition that often exists when the soil is below the water table or sea level, then water fills the gap between soil grains, or what we call the pore spaces. In response to soil compressing, the pore water pressure increases, and the water attempts to flow from the soil to zones of low pressure, usually upward towards the ground surface. So pataas, like in the figure a while ago. So by the way, the silt material or yung silt or clay, napakaliit ng grains niyan. Kaya kapag napakaliit ng grains, of course, napakaliit ng pore spaces. So gaano kaliit yun? It is less than 0.074 millimeter. Mas maliit siya sa 1 mm or 0.074. So napakaliit niya. And then between 0.074 millimeter up to 4.75 millimeter, that is granular material, or less than 4.75. Okay, that is granular. Yun yung tinatawag na sandy soils. Ngayon, kapag mas malaki na siya sa 4.75, ito na yung gravel, or what we call gravelly soil. So take note of the size, 0.074 for the silt or clay, or less than 0.074, 0.074, mas maliit pa siya sa 0.074, but not equal to 0.074, that is silt or clay. And then ranging from 0.074 up to less than 4.75 millimeter, that is a granular material, or what we call sandy soil. And then a size of greater than or equal to 4.75, that is gravelly soil or gravel. Okay. So if the loading is rapidly applied and large enough, or is repeated many times, ito ning cyclic. So it is repeated many times, such that the water does not flow, nandun pa rin yung flow or water out before the next cycle of load is applied. The water pressures may build to the extent that it exceeds the force between the grains of soil that keep them in contact. So these contacts between grains are the means by which the weight from the buildings and overlying soil layers is transferred from the ground surface to layers of soil or rock at a greater depths. This loss of soil structure causes it to lose its strength or the ability to transfer the shear stress, and it may be observed to flow like a liquid. So this is what we call liquefaction. So we can see here, kung may air entrapped sand, hindi pa floating ang ating lupa in water. But if it is fully saturated, mas marami ng tubig kaysa sa lupa, there will be a liquefied sand. So tendency is settlement. So there are soil liquefaction in the past that brought the attention of the scientists. So dito nagising ang mga scientists about this phenomenon. As an example is the 1964 Niigata earthquake in Japan. Okay. So imagine 2,000 houses were totally destroyed. Ang kagandahan, 28 lang ang namatay. Okay. So tsunami triggered by the movement of the seafloor associated with fault rupture totally destroyed the port of Niigata. So as in the picture. So the Niigata earthquake together with Alaskan earthquake, sabay sila 1964, brought liquefaction phenomena. So kitang-kita na dito nag-tilt yung mga building. Okay? So failure pa rin yan. So, this is our extreme tilting. So this earthquake also caused sand boils, the fissures. Yung sand boils, fissures, mga butas-butas because of the loosened material. So meron din tayong tinatawag na lateral spreading, caused the foundation of Showa Bridge to move laterally so much that the implied supported spans became unseated and collapsed. So floating na yung mga foundation niya. Wala na siyang pinapatungan. Pumatong man siya, hindi na kayang saluhin ng lupa. That is why nag-collapse. Okay. So another tragic event occurred in 1989, Loma Prieta earthquake. This is characterized by liquefaction. So the shaking lasted for 20 seconds lang. So what is the magnitude of this? So it is 6.9. So 6.9 magnitude. Okay. So 63 people were killed. 3,700 plus ang na-injured, and 12,000 people were displaced. Okay. So that is the earthquake at Loma Prieta. By the way, the epicenter of that is on the San Andreas Fault, which is 56 miles south of San Francisco. So, a building in the Marina District at Beach and Divisadero settled onto its buckled garage supports. Pag nagsettle kasi yung poste mo, it will follow. Your column will also buckle. So we also have the 1995 Great Hanshin earthquake. On January 1995, this is a major earthquake struck the city of Kobe, Japan. Kaya nga ito yung tinatawag na Kobe earthquake. So it killed more than 6,000 people dead, no? Casualties, which caused also 45,000 people homeless. So the Kobe quake was a result of an east-west strike slip fault where the Eurasian and Philippine plates interact. So again, it lasted for 20 seconds. So yung magnitude nito is 6.9, 7.3 on the Richter scale. Okay? So 30,000 yung injuries because of this. So imagine in the picture here that a collapsed expressway, tumagilid. So that is so devastating. So the strong ground motions that led to the collapse of Hanshin Expressway also caused severe liquefaction. Okay. So we can see here the damage to port and wharf facilities as can be seen to the left and below. Okay. So we also have the 2010 or mas recent to, no, 2010 Canterbury earthquake. So this occurred last September 2010. The Canterbury region was struck by a large earthquake causing 185 deaths or casualties. So marami ring na-injured, 164 seriously injured, and the total injuries is about 1,522,000 injuries. So by Richter scale, this is 7.1 in magnitude. So as a result of that earthquake, meron mga aftershocks. So results of liquefaction. Kitang-kita nyo, lumubog na yung mga sasakyan. And also, the aftershock caused, ito after 1 year, 2011. Okay. So 2011, we have the collapsed Pine Gold building. Okay. So may mga na-trap dito sa loob because of that earthquake. And that is a result of the aftershock after how many months? So we can see here now that based on the conditions of excess pore water pressure increase, kapag tumaas yung pore water pressure, hindi maganda kasi bababa yung effective stress. Okay? So ito yung tinatawag na soil liquefaction. But two distinctly different phenomena are incorporated into a single definition because the phenomena can have similar effect. Mahirap i-distinguish yung dalawang phenomena na cyclic mobility and flow liquefaction. So these are the main categories. So we have here the matrix that distinguish the two. Under flow liquefaction and under cyclic softening. So we have cyclic liquefaction as well as cyclic mobility. So pag sinabing cyclic, paulit-ulit. So what are the differences? In terms of loading conditions, okay, saan ba nag-cause ang flow liquefaction? Static or cyclic loading? Saan ba nag-form ang cyclic liquefaction? Ito. Cyclic with stress reversals. Okay? So, diniscuss natin about reversal. And then, cyclic mobility. It is cyclic without stress reversal. So, on the drainage condition, all of those may tubig. Okay? May tubig. And then, in terms of soil response to shear, we have variations. We have strain softening for flow liquefaction, strain softening and hardening for cyclic liquefaction, and then strain softening and strain hardening for cyclic mobility. So the controlling stresses here for flow liquefaction is static shear stress, and for both cyclic softening we have static and cyclic shear stresses. So the induced stress state, in situ shear stress greater than minimum undrained shear strength. So maganda pa to, flow liquefaction, kaysa dito. Because ito, effective stress state reaches essentially zero. So kapag walang effective stress, there's no capability to transfer shear stresses on the layers. So cyclic mobility, zero effective stress does not develop. So failure or deformation potential. For flow liquefaction, sufficient volume of soil must strain soften. Failure can result in slide or flow depending upon internal geometry and stress state. For cyclic liquefaction, strain softened shear modulus can lead to large deformations during cyclic loading. Soil will tend to stabilize upon termination of the cyclic loading. Now, for cyclic mobility, we have limited deformations unless very loose soil results in flow liquefaction. Okay? So, ito yung worst cyclic liquefaction in terms of potential deformation or failure. So, the soil types on flow liquefaction is any metastable saturated soil. So, very loose granular deposits, very sensitive clays, and loose deposits. For cyclic liquefaction, the soil types, almost all saturated sands with limited deformations in clayey soils, the same as cyclic mobility. Okay, so moving on to the effects of liquefaction, we have first, sand boiling. When liquefaction occurs below the surface that is fully compacted, the water pressure below the surface makes the water to break out like bubble. So this come out as boiling water. This is called the sand boiling. Okay? So may mga exit kasi sa surface and yun, tataas yung materials. And then secondly, we have the damage to offshore structure as an effect. So liquefaction is a common in soil that is submerged These conditions cause huge damage for bridge constructions, structures supporting submerged soil deposits. Yung mga submerged. Usually yung bridge, of course, submerged yung foundation niya. Meaning, there is a phreatic zone. Okay? So, remember the phreatic zone? May portion na may groundwater table. And then number 3, failure of dams and retaining walls. The soil supporting dams and retaining walls undergoes liquefaction, which results in the collapse of these structures. As the structures lose the ability to control the huge water, it further results in floods that are uncontrollable. Surface landslides. So the failure of water carrying bodies can result in surface landslides. So this is true kanina. Balikan natin to. The failure potential for flow liquefaction is that failure can result in slide or flow depending the internal geometry and stress state. So depende siya sa soil material. So landslide yan. Okay? So that is surface landslide. And then number 5, failure of structures under earthquake. Liquefaction followed by earthquake forces make the structure to lose its stability. They can either split or lean, bringing complete collapse of the structure. Past earthquake records have shown a huge failure of building structures due to liquefaction. These hazards do not provide enough time for evacuation that it results in a huge loss of life and property. So, ang kahirapan kasi dito sa liquefaction hazards, yung after effect niya is the liquefaction ng earthquake. Tendency, walang caution. Okay, hindi ka na makaka-exit, nag-collapse na yung building. Okay. So, after liquefaction, the soil no longer behaves as an active grid of particles. The strength and stiffness of the liquefied soil are significantly decreased. Take note of that. Often resulting in a variety of structural failures. Hence, a liquefied ground is no longer considered stable and fit for construction of structures. So, kapag liquefied ground na yan, huwag mo nang pilitin unless you are going to have a remedial measures or engineering work to improve the ground conditions. In a while, we will discuss the ground improvement techniques. Okay. So, it has no ability to take even its self-weight. Hindi niya na rin mabubuhat yung kanyang sarili because of liquefied conditions. The building structures constructed over such a deposit type lean and fall as shown in figure. Ito na. Failure of building structure due to soil liquefaction. So this is a liquefaction in Izmit, Turkey. It's very necessary to know the importance of the study of liquefaction. So, meron tayong adequate precaution before constructing a building. So, understanding liquefaction, chances of the soil helps to decide what treatment method is to be chosen to make the soil liquefaction free. This hence helps to have stronger and safer construction of the structure. So what can we do? So there are methods reducing soil liquefaction hazards. First, i-avoid na natin. So, wag nang magpatayo ng building doon if we cannot improve the ground. So, of course, the prerequisite for that treatment is the ground investigation. So, construction on liquefaction susceptible soils is to avoid it. It is required to characterize the soil at a particular building site according to the various criteria available to determine the liquefaction potential of the soil in a site. So second we can do is build liquefaction resistant structures. In certain situations, the construction over a land which shows the chances of liquefactions are not avoidable. Hence, foundation structures constructed must be designed such a way to resist the effects of liquefaction. The major reasons for constructing structures over liquefiable soil are space restrictions, favorable conditions, and other reasons. Actually, we have two options in dealing with liquefaction. If we could not possibly improve the soil, then find a way that your structure will resist the effects of liquefaction. And then finally, we have to improve the soil. So this involves mitigation of the liquefaction hazards by improving the strength, density, and the drainage characteristics of soil. This can be done using a variety of soil improvement techniques. Ito, we have here a simple diagram wherein there are measures to prevent the occurrence of liquefaction. So by principle, if we need to increase the density, ang method dyan is densification method. So there are a lot of methods of execution. We have sand compaction pile, vibro rod method, vibro flotation, dynamic consolidation, vibratory tamper, compaction by roller, compaction by explosion, group pile method. Okay, that is the densification method. We also have solidification. Solidification method includes deep mixing method, injection method, weak lime pile method, pre-mixing method. Next, part of the improvement of soil properties, adjustment of grain size distribution. We're gonna replace the material. Yun lang, replacement. And then lowering of the degree of saturation. Of course, we are going to lower the groundwater table. Meron tayong deep well. Kapag nag-deep well kasi tayo, bababa yung water table. Okay? And we have the dewatering by trenches. Okay. So another under improvement of conditions for stress, deformation, and pore water pressure. So we tend to increase the effective stresses. So we increase horizontal earth pressure, and then dissipation and control of PWP or the pore water pressure. Okay, so the principle or the method is dissipation of excess pore water pressure. So puro drain yan, no? Drain piles, gravel drain, and drain pile or artificial material. Why gravel? Kasi nga yung gravel, malalaki yan. So malalaki rin ng pore water dyan. Dyan gustong dumaan ng water. Okay? So water can flow easily or percolate or permeate sandy or gravelly soils. So we also have the drain installation for the surrounding area. We have the combined compaction with sheet piling. and sheet pile with drainage function. When we have a sheet pile, of course, we intend to divert the direction of flow. So we also have the principle inception of pore water pressures, control of shear deformation. All of these are linked. So the method is shear strain restraint method. We have the underground diaphragm wall. Okay. So measure to reduce liquefaction, induce damage to facilities. So paano natin mababawasan ang damages to facilities? We have supported by firm ground, the pile foundation. So if we intend to strengthen the foundation, strengthening of pile and spread foundation, and then strengthening of quay wall, reduction of lift of structure, so lift prevention pile or sheet pile for underground structure, or we can have constraint of surroundings. So by principle of flexible structure for ground deformation, we have the method absorption of ground deformation by flexible joint. And then we have the control of deformation after liquefaction. We have these methods: provision for supplemental foundation for mat foundation, reinforcement of mat foundation by geogrid, sheet piling for embankment. So this is a good reference for us. Ano bang gagawin natin? So may mga principle dyan, may mga method, at yung method of execution. So hindi basta-basta namimili. Okay, there are a lot of cases, especially during these times, marami nang lumalabas na study at hindi yan na nakikita sa textbook. So it can be seen more on literatures or experiments and scientific methods. Okay, so these are now some principles, a concrete principle to improve the ground. Okay, so if we intend to increase the undrained cyclic shear strength, it can be obtained through a more stable skeleton of soil particles. So, ma-achieve natin to by solidification method. Yung nabanggit kanina, solidification. Ito yung tinatawag na compaction grouting. So, by the figure, you can see, drill muna tayo sa pinakababa. And then, mag-inject ka ng grout pataas. Tapos. So, what is the essence of this? Of course, it will have a remediation of the loose particles. Hence, it will solidify the soil. So, such method is applicable even for foundation ground beneath an existing structure. Kung nakita mo na yung footing mo nakalatag dyan at may space sa baba niyan, you can do this one, or what we call the compaction grouting. Okay? We can also have, if we intend to improve the resistance to deformation, we can employ the underground diaphragm walls. So the surrounding the liquefiable soil with continuous underground walls. Okay. This method can be used for the soil at the bottom of existing structures. where liquefaction remediation is difficult using other methods. So in the diagram, you can see the method. Number 1, magkakaroon siya ng guide wall. Ipapalok yan. And then, secondly, may excavation, yung pagpalok. And then, stalling the top ends and bubuhusan. So, that is the underground diaphragm walls. Usually, it is used in buildings. We also have here, if we need to dissipate pore water pressure, we will just use the principle of yung capillary. Tusukin lang natin yung tubig, especially in clay. Okay? So, yung clay, mahirap pigain ang tubig sa clay. It will take you long years. Okay? But with installation of, I think this is weak drains. Ito yung weak drains, ano? Para siyang sheet na may mga butas. Of course, if we're going to insert that one, madadivert yung tubig. Of course, madidrain. So, merong internal draining. Pag tinusok mo yung clay, tataas yung tubig. Pero pag tusok mo, hindi tataas yan kaagad, of course. So, by principle of capillary, it will take months to drain. And then, usually, nilalagyan yan ng coarse material above. Bakit? Kasi susundin ng tubig ang coarse material because of the pressure. Okay? So, siya dadaan sa mas permeable na materials. Okay? So, the pore water will migrate into the weak drains so that yung excess pore water tatanggalin natin sa clay. So, if that happens, hindi na magiging undrained. Magiging drained na siya. So, mas maganda yung condition ng soil. Okay? So, those are some basic principles that you need to understand. Ano? Of course, our topic here is just limited to those enumeration and a brief introduction of the methods in dealing with liquefaction. So we can expound this by yung geotechnical engineering nyo later on. Okay? So with this, we can end our session for today. And good day, everyone.